Okay. So there is a change in schedule today. So I'll be conducting today's lecture of machine learning, and tomorrow's lecture will be conducted by Sir. So we'll in today's lecture we'll finish our discussion with the logistic regression, softmax regression that we had started yesterday, and we'll also talk a little bit about perceptron in machine learning algorithm. What is perceptron and a basic introduction to perceptron. So I'll wait for 2 minutes for everyone to join, and later on I'll start. Okay. Okay, I suppose everyone has joined the meeting. Let me share the screen now. So let us first just revise what we have studied so far. So in the case of logistic regression algorithm, we have studied that logistic regression is a classification algorithm. And so far, till the previous lecture, our discussion in the logistic regression algorithm was based on binary classification, which is a two-class classification, which will involve 0 and 1 class. Okay. So for example, yes or no, or cat or dog, these are binary classification problems that we discussed so far. So what we did in the binary logistic regression, we defined our hypothesis function, which is h of x is equals to 1 upon 1 plus e raised to minus z, which is a sigmoid function. So what is it doing is we are actually, what is the main motivation of logistic regression algorithm is we are trying to find a decision boundary which separates our positive and negative samples. And one of the assumptions that we have made in the case of logistic regression is that our data is linearly separable. Linearly separable means we can draw a line between these two data to separate it. For example, data which won't be linearly separable will be of this form. For example, these are your positive samples and these are your negative samples. In this case, logistic regression cannot be applied. Okay, so we went through this. In the case of linearly separable, we defined our hypothesis function for binary logistic regression. Okay, we defined our hypothesis function for binary logistic regression, which is of the form sigmoid function, which is a sigmoid function. And it what it does is, for example, you will be calculating, first of all, you will be calculating z value, which will be a weighted sum of your features. Weighted sum of your features means features will be your x1 to xn, and we'll be assuming x0 as 1 always. So, and it will be weighted sum means theta 0 plus theta 1 x1 up to theta n xn. What number of features that you have? It will be weighted sum of all your features. And then later you will be applying a sigmoid function on this weighted sum so that your output is squashed between 0 and 1. So what is this output that you'll be getting is a probability value that will be obtained. A probability value. And how do you read this probability value? For example, if you are trying to classify a data as tumor and non-tumor data, okay, you are trying to perform this classification on your data set. So if your h of x value is equals to 0.7, then this result is actually the probability that your sample instance is tumor. This actually gives the probability that your instance is tumor, that it belongs to class 1. That is what it is giving. So h of, for example, this is actually probability of 1 given x is equals to 0.7. So probability of 0 given given 0 given x would be 0.3, because the total probability value is equals to 1, right? Okay, so we discussed this, and later on we started with define the loss function in the case of binary logistic regression, and we also defined the gradient descent optimization. For gradient descent optimization algorithm, we derived the formula for gradient descent optimization algorithm in the case of logistic regression, which is quite similar to that of linear regression. The only difference in the case of logistic regression is you are utilizing a different hypothesis function. Okay. Also, we saw that MSE loss function. Yes, Janil, you have a question? Yes, right. Okay, all right. So you are saying that h of x is different, right? So we also saw that MSE loss function cannot be used in the case of logistic regression, because MSE loss function will give a non-convex result. Okay, we already have discussed about convex and non-convex in the case of when we were discussing linear regression, right? What is a convex function and what is a non-convex function? Later on, we also saw the regularization in the case of logistic regression. Regularization is utilized whenever we are having an overfitting data set. Whenever your data set is overfitting in your model, at the time you will be utilizing regularization, which is lambda times theta square. Okay, so this is what you will be adding. This is ridge regularization, and we have another which is lasso regularization, and both have their own significance in the case of overfitting, right? So this is what we discussed so far. Then we started our discussion on softmax regression. Okay, softmax regression, which is another form, which is you can also call a generalized form to your sigmoid function. It is a generalized form. Whenever you have more than two classes. So far we discussed in the case of logistic regression, our discussion was based on binary classification. But when we have more than two classes, at that time will be applying a softmax regression on your data set. Okay, softmax regression will be applied on your data set. So what is softmax regression? In this case, your hypothesis function is defined as h of x is equals to e raised to zi upon summation of I is equals to 1 to c e raised to zi for c. Means, c here refers to the classes. So for example, if you have 3-class classification, then your h of x in your output, that is y hat, that is your output hypothesis, you'll be getting 3 values. You'll be getting 3 values, where this value will be equals to e raised to z1 upon e raised to z1, e raised to z2 plus e raised to z3, and this will be e raised to z2 upon e raised to z1, z2, and z3. And similarly for the third, right? So this is what your output will be, and maximum, whichever is your maximum probability value, that will be considered as your class. That will be considered as your output class. So for example, if you're trying to classify between dog, cat, and horse, and this is the output that you're getting. Y hat, in the Y hat, you're getting output something like this: 0.75 for dog, 0.15 for cat, and 0.1 for horse. Then your output probability, whichever has the maximum output probability, that class will be considered for your input data set. Okay, input instance, whatever input that you're passing, that class will be considered. Okay, I suppose this is up to this, it was clear, right? And then we later on also discussed that how it will be performing. So for example, if your data set is something like this, x1 and x2, and this is your y output, and you have 3 classes in the y output. Suppose 0, 1, and 2. These are the 3 classes in your y output, and you have certain data set that is given in your x1 and x2. So what it will do it will create a one hot encoding. One hot encoding will be done whenever you are implementing using a scikit-learn library. This is the inside process that will be happening on each unique class label to separate dog and non-dog. Okay, so you want to convert this into two class classification. That is what you are saying. Yes. Okay. See, that is I. Okay. Then you need to fine, but I'm not aware of this. But what is happening in this particular point, if you see, is it is actually giving you output on the basis of three class classification. But I think in that case, for each class label we do this. For each class label. Okay. So you are trying to do what you are trying to do is you are saying is you want to convert this into a sigmoid form. That is, you want to convert this entire data set. So then you have to make changes in the data set, I guess. That is what you will be. So for, see, what you're trying to say is you want to convert this. For example, we have three classes, 0, 1, and 2 classes. But what you want to do is, suppose you are specifying the 0 as dog class and rest of the class as cat. But you in the output, you wish to have only two outputs, that is dog and cat. Dog and non-dog, right? So you want to put this whole into one class. That is what you want to do. But I suppose in that case, you have to make changes in the data set. So far as much I know, yes. So far as much I know, then you have to make changes in the data set to obtain a sigmoid output. But what we are trying to do here, why we are using softmax, is we want to obtain the probabilities for all the classes that we have. So we have three classes here: cat, dog, and horse. Okay, three classes we have, and for three classes we are obtaining the probabilities for each classes. And also, if you can see, this will be a tiresome process on the data set also. So if you each time what you have to do, you have to separate the classes in the cat and non-cat, and then you have to find out whether horse and non-horse. That will be a tiresome process. So that's why we'll be introduced to a softmax regression, so that this makes easier. So directly from all the probabilities, because if you see the output, in the output what will be happening is the sum of all the probabilities will be equals to 1. So automatically the maximum probability, you can state that the whichever has the maximum probability, that will be your class output. Are you saying? Yes, Janil? Is that, are you getting the point? Yes? Okay. Fine. I suppose that the answer is satisfactory. Shall we proceed? Just a minute. Okay. So our discussion was, what were we discussing about softmax regression? So in the case of softmax regression, that is what we discussed, that in the output that you will be getting is three values. That is, for each class you will be getting certain probability values, and the total of this probability values will be equals to 1. And all these probability values will automatically will be between 0 and 1, right? Now, in this case, I suppose everyone is clear with this idea. Anybody else having any doubt in this particular point so far? Please unmute yourself and ask the question, or you may also ask in the chat box. Okay. All right. So now, in this case, if you see, there will be multiple parameters that we have to study. Multiple parameters. Since we are getting three outputs, here we are getting three outputs. So in each case, we'll be studying multiple parameters. Okay, three outputs, we'll be studying multiple parameter value. So in what will be happening is, we will be creating so if you remember, what was the loss function in the case of for binary logistic regression? What was the loss that we had is minus of y into log of y hat plus 1 minus y into log of 1 minus y hat. Okay. Yes, right. In sigmoid, this was our loss function. So if you see, in the case of softmax, we'll be having a generalized loss function. So whenever you are implementing with scikit-learn library also, if you state the number of class equals to 2, automatically this will be the loss function that will be implemented. But whenever you have more than two classes, your loss function will be something like this. It will be summation of I is equals to 1 to m y k into log of, sorry, k, y k log of y hat k. So suppose if you are implementing, so this will be your loss function in the case of softmax regression. In the case of softmax regression, this will be your loss function. So suppose you are implementing for binary class classification, binary. So what will be happening? Your y total, your number of classes is equals to 2. So automatically your y total of y will be equals to 1. Okay, your output. What is k? K is the number of classes. K is the number of classes. Okay. So automatically your loss function will be converted to what it is in the case of binary logistic regression. Okay. So what will be happening is, for example, if you see, let us take an example. What will be happening here is, let us take an example. For example, x1, x2 we have, and we have a y output of 3 classes, where we are, suppose x11, x12. So what will be happening for y? We'll be generating 3 y's here, which will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so your loss function, in this case, for each row, you'll be having a different loss function, yes or no? For each row, you'll be having a different loss function. So for first row, your loss will be y1 of 1 log of y1 hat of 1. This is for 1. This is y1. Okay, plus y1 of, this is for row. This actually refers to row, and this actually refers to your this actually refers to your y2. This refers to row. Okay, so it will be y21 log of y21, y hat 1. So don't get confused. Let me just write this first of all. Later on we'll discuss. Okay, so see, this is for first row. Okay, row number 1, I'm writing the loss function. Your entire loss function will be sum over all the training samples. Okay, right now I am just writing for one of the training samples what will be the loss function that will be defined. So in this case, you can automatically see that y2 and y3 will be equals to 0. Yes or no? These two values will be equals to 0. So automatically this loss function will be based on your first output, that is for class 1. Okay, similarly in the case of third row, second row, and third row. Are you getting the point? So automatically whenever you are applying the gradient descent on this particular value based on these, estimating parameters based on this. For example, your first, for this, for example, W0, W1, and W2. These are the parameters that I'm referring to. So it will be, for first class will be having certain set of parameters, and for second class will be having certain set of parameters, and for third class also will be having certain set of parameters that will be estimating. Okay, are you getting this point? Yes or no? Or it is confusing? Okay, is everyone clear with this, what we are trying to do? So we are using here a generalized, yes. Okay, let me come again. Okay, so let's just go back to what we did in your output. For example, 3 class classification. At this point of time, I'm talking about 3 class classification. So you'll be getting 3 outputs in your output, the hypothesis function based after applying a softmax function. So now, what is the loss function in the case of softmax regression? Loss function will be a generalized loss function that you'll be getting. So it's just, so loss function in the case of softmax is L is equals to summation of I is equals to 1 to K. I is equals to 1 to K YK of YK into log of YK hat, where YK hat is your predicted value and this is your actual target value. Okay, actual target value, and K is your class. Okay, this is your loss function that you have. Now suppose for entire training data set, also I forgot to mention the minus. For entire training data set, your loss function will be summation over all the training samples. So it will be 1 upon sigma I is equals to 1 to m, 1 to k, yk of I, log of yk of I. Okay, this will be your loss function. This is your generalized loss function in the case of softmax regression. So whenever we have two-class classification, so if you remember, what is for two-class classification? It will be automatically k is equals to 2. Yes, k will be converted to 2, and automatically it will be y1 log of y1 plus y1 hat plus y2 log of y2 hat. Okay, but you can also say that probability. You can also say that y1 and y2. What is y1? Y1 will be 1 and y2 will be 0. So you can also say that y2 is equals to 1 minus y1. Yes or no? Y2 is equals to 1 minus y1. Can you write like this? Are you getting my point? So in two-class classification, we have only two outputs. Either y is equals to 1, either y is equals to 0. So here, if you implement this loss function will be converted automatically, k value will be equals to 2. K is your class value. Okay, number of classes that it is mentioning, number of classes. So if you see, if y1 is equals to 1, I am keeping y1 is equals to 1 and y2 is equals to 0 because we have only two target values that is possible, either 1 or either 0. So we can also say y2, we can also write y2 as 1 minus y1. Yes or no? We can write it as 1 minus y1. So it will be converted into y1 log of y1 hat plus 1 minus y1 into log of y2 hat. Y2 hat is actually what? In two-class classification, we'll be getting two values. Here one value, here two values, second value. Okay, two values that we'll be getting, and the total sum will be equals to 1. So we can also write 1 minus y1 hat. So it will be automatically, this loss function will be automatically converted into binary logistic regression whenever we have two classes. Okay, that is clear to everyone. This point is clear. Now Priyank and all others, is it clear now? This point is clear. I'll proceed with the next point now. Okay. Now after this, so what will be your this you can say this is your generalized loss function. So which is defined in the case of softmax regression. So whenever you have more than two classes, sorry. So your loss function will be minus of summation I is equals to 1 to m, total number of samples in our training samples. I is equals to 1 to k by k I and log of yk I hat, which this is your predicted value and this is your actual target value. Okay. So now what I'm trying to say is whenever you have a training sample, something like this, x1, x2, and this is x11, x12, x21, x22, x31, x32. And this is your y, which is of class 1, 2, and 3. Then after this, since we have three classes, we'll be converting it to one hot encoding. So it will be y1, y2, y3, 1, 0, 0, 0, 1, 0, 0, 0, 1, something like this. So your loss function will be, what? For example, if you're calculating for only first row, then if you apply this, I is equals to 1 to m. I will be eliminated at this point of time because I'm considering only the first row. So it will be y1, y1 of 1. This I is actually the row value, y1 log of y1 hat of 1 plus y2 1 log of y2 hat of 1 plus y3 hat of 1. Y1 is actually mentioning the row. Okay, so this 2 will be automatically equals to 0. Yes or no? Because y2 and y3 values are 0 here. Minus 2 of 1 minus y hat. I think Janil, This definition is clear. I think you have made some mistake in -2 of, because we are having two different y2 and y3. No, no, no. Okay, no, no, no. See, we cannot write like this because we have y1, y2, and y3. Now here, I think that is what you are trying to say, that here y2 is equals to this, but no, need not write like this. We can directly place it as 0. In two-class classification, I was just mentioning that you can write in the form of binary logistic regression. But ultimately, this will be equals to 0. Whatever equation you have put, it will be equals to 0 only, if you see. Yes or no? So these two values will be equals to 0. Yes, right? Okay. So now what I'm trying to say is, whenever you are applying a gradient descent algorithm on this, okay, up to this everyone is clear. Whenever you are applying gradient descent algorithm, okay, we'll be learning different parameters. So for example, here we have three different classes. So for each class, we'll be learning different parameters. So here, okay, voice is cracking. Okay. All right. Is it coming clearly now? Okay. So what I'm trying to say is, for in the gradient descent algorithm, we'll be learning all the parameters value, learning all the parameter value. For different classes, we'll be learning different parameters value. So since here in this whenever you are applying using scikit-learn, this is what will be happening. So you will be creating the loss function and you will be applying a gradient descent algorithm. Later on, you will be applying a gradient descent algorithm to learn these parameter values, which are theta 0, theta 1. These are your parameter value. And for each classes, you'll be learning different parameter value, so that you'll be in the output, you'll be getting different y hat value. So for 3-class classification, we'll be getting 3 y hat values here. And for 2-class classification, we already know how to implement binary logistic regression, right? So everyone is clear with this point, yes or no? Yes, is everyone clear with this? Okay. What about others? So after this, I'll proceed with one more point and then we'll start with perceptron. So if anybody is having any doubt, please mention it. So we'll proceed. Okay, please, okay. See, okay. Up to this, everyone is clear. So we are having this y1 hat. This is what for the first row. This is what you'll be having. This is the loss function that you'll be having. Okay. Till loss, it is clear. Okay. This is what for the first row. And in the yesterday's class, if you recall, we had discussed about something called parameters. For each of these classes, each of the classes, for each of the classes, we'll be having Z1, Z2, and Z3. Yes or no? We were having Z1, Z2, Z3, if you recall. In the yesterday's class, we had discussed about Z1, Z2, and Z3. So in the similar manner, whenever you are lost, so here you can see in the case of loss function for the first row, you can see that your first row 2 and y3 was eliminated. Y2 and y3 was eliminated. So what we'll be learning after the loss function, what will be happening? It will be actually after you calculate the loss function and you apply gradient descent, what it will do for the first for the based on these classes, whatever data set division that is happening, it will try to learn the parameters accordingly. So for Z1, what is the parameter that it will be learning? Let us refer to theta 0. So theta 0, theta 1, and theta 2 are the parameters that will be learning. But for Z1, it will be learning based on class. Okay. For Z2, it will be learning based on class 2. Similarly, for Z3. That is what I'm trying to say. Is it clear now, or still having any doubt? Yes, now is it clear? Okay, that is what I'm trying to say, because what we'll be doing, after applying the loss function, we'll be studying for the gradient, and gradient is used to find out the parameter value to find an optimal decision boundary. That is what we are trying to do. And later on, it will be what is gradient descent algorithm will do, it will try to learn these parameters. Okay, these are the parameters that will learn. So here we have class classifications. These are the parameters that will be learning. Based on multiple class classification, more number of parameters will be added to be learned. So we have in the softmax, since we have the output something like this. That's why there will be multiple parameter learning here. Okay, I suppose now is it clear? Everyone is clear with this? Yes or no? Okay, fine. Here, after studying softmax regression, here our discussion on logistic regression is over. One more discussion on logistic regression is complete. I suppose that everyone is aware about stochastic gradient descent. Is everyone aware about stochastic gradient descent algorithm? Yes or no? And also, for your reference, I have uploaded the PPT for logistic regression. In yesterday, I have uploaded the PPT. Did anyone go through the PPT yet? Anyone went through the PPT? So we were actually having lecture tomorrow, but since we have shifted it today, so did anyone go through the PPT? And I have also added some of the references which you can refer for the further study, which I had it, some of the YouTube channel links as well, which you can study for easy understanding. So I suppose that that will be helpful. So did anyone go through the PPT yet? Okay, not yet. Fine. See, all right, that's fine. But go through the PPT by today or tomorrow, and you may also ask me through mail if you have any doubt in the understanding any of the concept before the because we have exam on Monday, I guess, right? All right. So fine. So everyone is aware about stochastic gradient descent, yes or no? Stochastic gradient descent. Yes. Anybody has any idea stochastic gradient descent? I suppose we had discussed about this in the lab session when we were discussing about linear regression. We had a small discussion about stochastic gradient descent. Okay, fine. If you are not aware of this, let me discuss. So in the case of a normal gradient descent, what we are talking about, normal gradient descent algorithm that we are talking about, it is a batch gradient descent. Batch gradient descent means what? All the training samples will be considered whenever we are updating the value of parameters. Okay, all the training samples will be considered whenever we are updating the parameters. But there is a possibility that your training samples will be very high. Okay, 10,000 training samples, suppose you have 10,000 training samples, then it will be very time consuming to update each of the parameter value by going through the entire training sample. Yes or no? This will be a very time consuming. Yes, this is a batch gradient descent that I'm talking about. Now I'm coming to stochastic gradient descent. Okay, so what is happening? How to overcome this problem? That to whenever we have a large training sample, so it will be hard to perform the calculation on entire training sample. We have something called stochastic gradient descent, where it will be considering a single training sample. A single training sample will be considered to perform the update on the parameter. Okay, what is the idea behind gradient descent? You are updating the parameter. Gradient descent is actually what it is doing. It is actually theta j is equals to theta j minus alpha into del j by del theta. That is what it is doing. It is updating the value of parameter. In the batch gradient descent, what we are doing, we are going through the entire training sample. Here we are going through the entire training sample. If you remember, we had a summation symbol here. Summation over all the updates, a summation over all the updates that we are doing, right? But instead of that, to overcome this problem, we have stochastic gradient descent, where we'll be considering only a single training sample to perform the update. A single training sample will be considered to perform the update, which will be much easier to perform in comparison to batch gradient descent. Are you getting the point? What is the problem that we are solving using stochastic gradient descent? Is the point clear? Yes, yes, and also what will be happening? It will be if you see, it will be much since stochastic gradient descent, we are actually using only one training sample at a time. It may be also hard to reach the, yes, it will be slower because it will be hard to reach the global minimum at this point of time, because it may be possible it will try to retract somewhere else and then it will finally reach your global minimum value that you want to reach. But using batch gradient descent, it will be much easier, the path will be much smoother. But why we are using stochastic gradient? Because in this case you will be utilizing only one training sample, so it will be much easier. The time consumed will be much easier as compared to the what in the batch gradient descent. Is the point clear why we are using stochastic gradient descent? Yes or no? Yes? Okay. So this one point that I wanted to discuss in the case of stochastic gradient descent. What about others? Is it clear to everyone? Okay. Fine. All right. So now after this, we have finished our discussion on logistic regression. Classification as a classification, which is a classification algorithm. We have finished our discussion. Now we'll start with something called perceptron. Okay, perceptron, which is a basic neuron in your neural network. Okay, whenever we'll start our discussion on neural network, we'll study more about this in the neural network. But this is a basic neuron, basic node that we have in the case of neural network. So mostly in machine learning, what we try to do is we create a similarity. We try to draw a similarity between your brain neural network and the neural network that you are creating, that the neural network that you'll be building. So perceptron is a single node neural network, you can say. But in normal neural network, whenever you study in the deep learning, so far what we have studied is machine learning. Deep learning is one of the subset that we have in machine learning, in which you'll be having multiple neurons, and multiple neurons will be trained to on your training samples to create a particular output. And mostly deep learning can be used in the case of image classification. Whenever your data set is having image classification based problem, at that time we'll be utilizing deep learning or similar to that. And before that, we'll be studying about artificial neural network as well. Right now, we are just getting a basic idea what a perceptron is. Later on, after we finish our discussion on one other classification algorithm, which is support vector machine, we'll start our discussion on artificial neural network and convolution neural network. That is quite later. But first, today we are just getting an introduction to perceptron. Okay, that is what we are doing. Fine. But before we proceed, I hope that everyone is clear with everything with logistic regression. If you are still having any doubt, you may ask through mail. In this lab on Saturday will be conducted by sir, so I won't be there. But before that, you may ask through the mail or anything if you are facing any difficulty. So I would suggest that you go through the PPTs as soon as possible. Right? Fine. Okay, so for building your basic artificial neural network, perceptron is used. Okay, so it is similar to what we studied in the case of logistic regression. If you see, what we studied in the case of logistic regression is we were having certain input. So x1, x2, x3. Suppose these are the three inputs that we have, and we have x0 is equals to 1 all the time, and we have certain weight assigned to it. Weight means I am talking about parameters here. So in this case, we'll be having parameters which is w1, w2, w3. In this case, we'll be referring to parameters as weight. So for example, w1, w2, w3 are the weight assigned to it, and we have a bias term w0. All these values we are passing through, we are first calculating the weighted sum of these inputs. So weighted sum of this input will be w0 plus w1 x1 plus w2 x2 plus w3 x3. And then we are passing this weighted sum through a sigmoid function. This sigmoid function can also be called as an activation function, which is we are trying to estimate when this neuron will be activated. So we had assumed in the case of sigmoid function, if you recall, I had already discussed that if the value is greater than 0.5, then your output will be 1, and if the value is less than 0.5, your value will be 0. In the case of binary logistic regression, if you recall, yes, we had kept a threshold value as 0.5. So whenever the value is greater than 0.5, your output will be predicted as 1. And whenever your probability value is less than 0.5, your output will be predicted as 0. Okay. So after passing through sigmoid function, we'll be getting certain output y hat. So your perceptron is similar so the perceptron. So before so perceptron is having a similar structure. So in the case of perceptron, what we'll be having? We'll be having certain values x1, x2, x3. We are having x0 is equals to 1, and we are having a bias term. We are passing this data with some weighted values, w1, w2, w3. We are passing this and we are calculating the weighted sum of these values. And here the activation function that we'll be using is a step function. Step function means what? For all the values which are greater than equals to 0, we'll be predicting the output as 1. And for all the values which are less than 0, we are predicting the value as 0. That is what your output is in the case of perceptron. This is how your perceptron basically works. So perceptron, how it works, if the value of the step function will predict the output as what? If the value of z that you're estimating is greater than equals to 0, then your predicted output will be 1. And if the value of z is less than 0, your predicted output will be 0. Okay. Is this clear how the perceptron works? Is this clear to everyone? Yes or no? Okay, yes, I'll repeat the output part. So if you recall, in the case of logistic regression, your output was a sigmoid function. We were applying a sigmoid function on our output. On our output means what? The z value that you are getting, which is a weighted sum of your input and weights. We were applying a sigmoid function, and based on that, we were creating an output. But in the case of basic perceptron that we have, basic perceptron, what we are doing is we are applying an activation function that we are using here is a step function. Step function means what? Here, if the z value that you are estimating, z is w0 plus w1 x1 plus w2 x2 and so on. If the z value is greater than equals to 0, we'll be predicting an output as 1. And if the z value is less than 0, we'll predict an output as 0. Okay. That is what your perceptron is working. That is how your perceptron, basic perceptron is working. With a single node. At this point of time, we are talking about a single node perceptron. We are not talking about multi-layer perceptron, only a single perceptron that we are talking about. In this case, what we'll be doing, we'll be having multiple inputs along with the weights, and then we'll be passing through a z. We'll be calculating the weighted sum. We'll be passing it through a step function to estimate the output. Okay, estimate the output. Now, how, if you recall, in the case, this is having a certain backdrop. That is why we shifted to logistic regression and and in this case, we are using, and if you see, we are using a step. Then why we are, okay, output is, we require, okay, see, we require sigmoid. No, here, see, don't get confused. We are not using sigmoid in the case of perceptron. We are using step function as an activation function in the case of perceptron. Okay. And in the case of logistic regression, if you recall, our output is totally predicted based on the sigmoid function. And if you recall, why we already discussed that why we are using a sigmoid function, because your z value will be very much higher than 0 and could be very much higher than 1 and could be much less than 0 as well. And in that case, you cannot use a step function to perform a classification. That's why we shifted to sigmoid function, which gives us a probability distribution value. Okay. So in this perceptron, we are actually utilizing a step function. We are actually utilizing a step function here. So in this step function, if your z value is much higher than 0, you will be predicting y as 1 as an output. And if it is less than 0, we'll be predicting 0 as an output. In this case, you will not be getting probability values. Okay, you will not be getting probability values. Only you will be getting 1 or 0 as the output in the case of perceptron. Okay, is this clear? Yes or no? Okay. So now, so for example, what will be the algorithm? How it will work? So basically what we are trying to do, we are reducing the loss. So we also need to update the parameters. Updating the parameters is also required. So what will happen? Suppose in this case, the very simple algorithm is that to update the value of parameters. So for example, if you're so basically what it is doing is it is trying to create a line. Okay, based on perceptron, if you are trying to classify your data, it is trying to create a line between positive and negative samples. Okay, and for positive samples, the z value will be greater than 0. And for negative samples, z value will be less than 0. Yes or no? These values will be greater than 0 for all the samples which are on the positive side of this hyperplane, and all the values which are on the negative side of hyperplane, the z value, which is the distance. Okay, z value is the distance of the point from the line will be less than 0 for all these values, and will be greater than 0 for all these values. Okay. So what will happen? A simple update rule is being applied in the case of perceptron. The update rule is being applied in the case of perceptron to update the value of parameters. So for example, if your data, if your wi is xi, actually the data was of positive form, but your to 0, then what will happen? You will try to, it will be something like this. Just a minute. So if your actual data was in the positive, actual data, the actual target value was positive, but your predicted value is actually, predicted value means z. Z is the predicted value. And based on the z, we are applying a step function on this z to predict the output. And if your z value is giving the value less than 0, then what will happen? We'll actually update the weight is equals to w plus x. And this is actually a normal form. We'll also see a generalized form of this, which is of something of this form. The generalized form is something like this. Wi is equals to just a minute. Wi is equals to Wi updated value is equals to Wi plus alpha, which is your learning rate, into the actual target value minus output into xi. Okay, so for example, let us see. For example, if your classification, if your actual target value was 0, actual target value was 1, but your predicted target value, actual value was 1, and your predicted value was 0. So what will be your update value? W update is equals to Wi plus alpha into xi. Yes or no? Because t minus 0, 1 minus 0 will be 1. But if your actual, for let us consider, if your actual target value was 0, but your predicted value was 1, then W update will be equals to Wi plus alpha into minus xi. Yes or no? Which is ultimately W minus alpha xi. Are you getting this? Yes or no? Are you able to relate this point? Yes or no? Is everyone clear with this? So your algorithm will be something like this. Your algorithm, generalized algorithm will be something like this. If your point was in the positive plane, but your z value is negative, the predicted value is giving you negative value, then your update will be W updated is equals to old plus alpha into x. Otherwise, for example, if your x was in negative, but your z value is greater than equal to 0, then your updated value is equal to W old minus alpha x. This is a simple perceptron algorithm. Okay, simple perceptron algorithm is something like this. Okay, so one of the major drawback of this particular algorithm is it is not going to update the parameter value. It is not going to perform any update whenever your classification is correct. Okay, whenever there is no misclassification, there won't be any update to any of the parameter value. No update to any of the parameter value. That's why we can use some other activation function as well. Here we have used a ceph function as an activation function, which is only giving 1 and 0 as an output. But we are using, for example, in the logistic regression, we have updated this perceptron to give probability distribution value. Instead of giving 1 and 0 as an output, we are getting the probabilities of this particular data to be belong to one, to be belonging to the class 1. Are you getting this perceptron algorithm? Yes or no? This algorithm is clear to everyone? Yes or no? Is everyone clear with this? Okay, fine. So this is the basic idea of perceptron. And also, okay, so this is the basic idea in the perceptron algorithm. So in perceptron, what is the step activation function that we are using is, we are using a step function, which is actually giving us a threshold value where we are estimating if value is greater than equal, z is greater than equal to 0, output will be 1, and z is less than 0, the output will be 0. Says, for example, if you are trying to learn a certain algorithm, suppose suppose you are asked a certain question like this, like for example, if you are studying an or AND is an as in gate that you are trying to study, and suppose we are giving certain update w1 w2 and theta w0 values, then you may be asked that what is the update, what is the update after first iteration. Okay, after first iteration, what could be the update? For example, if you have a and b, 0 0 1 1 0 1 0 1, and your AND gate output will be 0 1 1, sorry, and 1. This is the output, and you can keep a threshold value like this. So if your value is greater than equals to 0, then it will be estimating as 1, and if it is less than equals to 0, it will be estimated as 0. And you'll be given certain w1 w2 and w0 values to estimate that what is the value of your z that you're getting for each of this, what is the prediction that you're getting for this particular parameter value, what is the prediction that you're getting for this threshold that I'm keeping. Are you getting the point, what I'm trying to say? Yes or no? Okay, fine. So here I'll stop the discussion further. So we'll be keeping up to this in your sessional exam. In your sessional exam, it will what all topics will be there is, you'll be having after our first session we discussed something about overfitting in the case of decision tree. Further 2 points were discussed, if you recall. In the case of post pruning, we discussed cost complexity pruning and pessimistic pruning. Okay, pessimistic pruning, these were the topics that we had discussed in the case of decision tree learning. Later on, we studied about ensemble learning models, and in that we studied about various ensemble learning. Most basic 2 ensemble learning that we recall is AdaBoost and random forest. Okay, in the case of AdaBoost was boosting algorithm, and random forest was bagging algorithm. Later on, we discussed for our classification algorithm, which is logistic regression, and we got a basic idea about perceptron. Okay, how the perceptron works. Okay, after the first session, we'll get more detailed idea in the case of perceptron, but up to this will be there in your sessional exam. So is this clear to everyone? Everyone is clear with this? Any doubt in today's lecture? Okay, so fine. What you do is, I have already uploaded. I suppose everyone others are also getting this. Those who are not responding in the chat box. And what you do is, today you study all the PPTs that I have uploaded. Try to understand the concept, and if you face any difficulty, you may email, communicate through email, and I might be able to solve it through email itself. Fine, but try to study and try to understand all the concepts that we have discussed in the lecture section, right? So I hope that you'll perform better in the mid-sessional exam. So I'm ending the meeting now, and good luck for your exam. Okay.